Can you hear me? Hopefully you can, unless your speakers are muted. But now we might have enough mathematical and physical understanding that we can now describe, to some degree, sound, or sound waves as we want to describe it. So one of the common examples of how we might do this is if we could somehow trace back sound to some sort of a simple harmonic oscillator. So springs, rubber bands perhaps, but those aren't usually as audibly noticeable to human ears. Instead, maybe one of the more common items that would be used in such a context is the tuning fork. These are designed such that you give it a good wallop on the side, and then it will start wobbling back and forth. And if you look very carefully, you can even see that wobbly motion. Now, in that case, then, if it's going to wobble and is going to move away from its normal standing point as much as it can, at that instant it will have stopped and then return back and go back and forth like that. So this thing is actually going to move back and forth like a simple harmonic oscillator. Now, how does that produce a wave? Well, in that case, then, we could say that if this thing were moving back and forth, it would be pushing on the air and produce basically little pulses in the air of higher density and then lower density. And if you want to prove that it is air, then if you were to put this tuning fork in some sort of a vacuum chamber and then suck all the air out, you would notice that it gets quieter and quieter until it's completely inaudible. So we know somehow that air is involved, and the way we would explain it then is this thing is vibrating, pushing on the air, and with that motion is creating pulses of high pressure and low pressure air, and at a very regular rate, so it would be a regular frequency, and that's how we're getting our sound waves. Now, if we wanted to determine the speed of sound, there are a number of different techniques that we could go about doing that, depending on if we're believing that sound does have some sort of a wavelength function. But if we look at the various measurements that we have, and if we assume a temperature that's close to room temperature, and the room temperature close to about 300 Kelvin, things will also be affected by atmospheric pressure. If it's a little bit higher or lower than norm, humidity can affect things, but the measurements we'll usually work with is we'll say that the speed of sound is about 343 meters per second. That's a pretty good speed. It's a little faster than I can run. Okay, it's a lot faster than I can run. And you usually need something like a jet plane of some sort to actually achieve speeds like this. So let's suppose again we have our tuning fork and we'll just put it at one point. We can then describe the pulses going out from there in concentric circles. So a pulse will happen at one moment, and it will move away at the speed of sound. And then there will be another pulse again, and in the time that that pulse is created, that first pulse will have moved out some amount, and those rings can go out greater and greater and greater. And this is, of course, we just keep the object stationary, and these concentric circles will be all of similar distance apart. Nice and simple. But we have a tendency that we don't just keep things in place. I might talk to you, and I might not stand still. A car might be coming, it will produce a sound, and it could be coming or going from you. So what would happen in that case? So suppose again we'll have our tuning fork moving along with some speed velocity v. So it will put out a sound wave, and it'll go again away from it in a nice concentric circle. But by the time that circle has then pulsed out, this thing will have moved forward. And so by moving forward, that concentric circle that then pulses out will meet where the old one was when it had its previous center. And you'll notice then what that means is that the distance between these two pulses is smaller in front, in the direction of the velocity, while in the back the distance between those two pulses is larger, and so on if we draw more and more pulses. So this is going to have the interesting effect that if these pulses are closer together, that means that the distance between those wavefronts, and so the wavelength, is smaller. And back here, the wavelength is greater. Now, remember, though, that the speed of sound, 343 meters per second, this is actually going to simply be a property of the air. And so it's unrelated to the pitch or the frequency of the sound. So this is going to be some constant speed of the sound. So in the front of the wave, if the wavelength gets smaller, the only way this is going to work then is if the frequency gets larger. And so we might say that it has higher pitch. While in the back, the wavelength back here is larger, and so the frequency needs to be smaller. This is in essence then what is the Doppler effect. And this is something you'll notice anytime if you ever hear an ambulance drive by. When it's coming at you, it's much higher pitched, and then when it's moving away, lower pitched. If you ever have a locomotive going by you, and you might have even, if not in real life, you've probably seen films with it, that sort of effect is what you expect from Doppler. So to describe what's going on here, the equation form is going to be something like this. You're going to have the frequency that is actually heard, we'll call f prime, and it should be related to the frequency of the sound that's normally transmitted. So if the thing weren't moving, you weren't moving relative to it, this is the sound you would hear. But there can be two possible different effects. The source of the sound could be moving towards or away from you, or you could be moving towards or away from the sound source itself. Both of those things are going to actually have an effect. So to add those two effects together, there's two things to consider. There is the speed of the source itself. There's also then the speed of the observer. And then how this relates then to the speed of sound itself. And I'll just leave the speed of sound as just v, because otherwise the subscripts can get a little bit confusing. And to be a little bit different from the book, I'm going to use a notation that might look a little bit unusual. So in the numerator I have plus minus, in the denominator minus plus. Why have I done that? So imagine this, if the source of the sound is coming at you, then we can say that that could be the positive direction, that velocity is positive here, and add that together and the numerator gets larger, and that means the frequency will go up. That's what you would expect. The thing comes at you, the frequency is greater, and if the thing moves away from you, then the frequency should go down. In that case, then this velocity is going to be negative. However, it's the opposite effect with the observer. If the observer is moving away from the source, then that's actually going to make the frequency lower. And conversely then, if it's moving towards the source, it's going to make it go higher. So in some ways then, while this person could be moving, say, towards the right, if we draw it like so, this is our source, and this ear, I claim it's an ear, is our observer, it's the way of hearing things. If this guy is moving this way, that would have a positive effect of increasing the frequency. But if our observer is moving in this direction, moving away from the source, still the same direction though, that's going to make the frequency go down, so kind of the opposite effect. So that's why I'm using here plus minus and minus plus to have that opposite effect. Now, to really get this straight though, probably the best way to figure if you want to put a positive or negative value here, if you want to add or subtract think of it instead this way. Try to intuit it of what do you expect to have happen if the frequency is supposed to go up. Then you want to have the numerator get larger or the denominator to get smaller. The denominator will get smaller if you're subtracting. The numerator will get large is if you're adding. And again, assuming all positive values here. And conversely, if you need the sound to go down in frequency, or if that's what you're expecting, that means the numerator should get smaller, the denominator should get larger. So if you think of it in that sort of intuitional sort of way, then you'll realize when you're supposed to be adding, subtracting, and to make it more obvious that way. But I leave this notation here just to say that two objects moving in the same direction will have opposite effects on what happens to the frequency. The key insight, though, to the Doppler effect is that this is something explained by a wave theory of sound, if believing sound is caused by pulses in the air. So something like this can then be pretty good evidence for why sound ought to be described as a wave versus some other mechanic. One last thing to consider when it comes to that speed of a sound. When I gave that as 343 meters per second, I said how it depended on the temperature of the air, atmospheric pressure, things like that. Why should that matter? Now think back to when we talked about mechanical waves, and so for example, if I had a string and I put a pulse through it and I wanted to talk about the velocity of that wave, I said how that velocity was determined by the tension and the linear density of the string. So let's think about then the case with sound. If I change the temperature, I end up changing the density of the air. And if the air is less dense, then there's less mass per unit volume. And so that's kind of similar to saying I'll make mu smaller, which then will make the velocity go larger. So then less dense air should have a faster wave speed, it would seem from that. Atmospheric pressure will be a similar thing, since if you increase the air pressure, you're going to also basically kind of crush the air a bit more and make it more dense. So that will affect the speed of sound propagating through. Humidity will also affect things because water molecules are not the same density, or will not have like the same density of air then as if it were dry air, which is then mostly nitrogen molecules, some oxygen molecules, carbon dioxide to a very small amount, those sorts of things. So this also means that if we were to change the medium, say to a different type of air, we could greatly change the speed of sound. So if we wanted to use helium, which is much lighter than normal air, then it's going to have a much greater speed. And instead, if we use argon, which is much more heavy, much more dense of gas than normal air that we breathe, it would have a lower velocity. Now, you've probably had a few parties perhaps, or you've seen things where then people breathe in helium and it changes their voice. Why do you then think helium would have that effect? This is going to be explained when we start talking about interference and then applying that to sound and then musical instruments.